So, have you ever seen this happen? An AI model that looks like an absolute genius during training. I mean, it's acing every test, nailing everything you throw at it. But then, the moment it faces new, real world data, it just completely fumbles. This huge gap between the lab and reality is one of the biggest hurdles in machine learning. So, let's dig into why this happens and, more importantly, how we can actually fix it.
And that really is the central question, isn't it? The problem isn't that the model is dumb, it's that it's not actually learning the deep underlying patterns. Instead, it's just memorizing the training examples, the noise, the quirks, all of it. So when it finally sees something new, it's totally lost. How do we get our AI to truly understand and not just cram for the test?
All right, here's how we're going to break it down. We'll start by really defining this memorization problem. Then, we're going to walk through 4 really powerful solutions: taming the model's complexity, forcing it into teamwork, creating more stable learning conditions, and finally, just giving it more varied practice. And at the end, we'll put it all together into a practical AI trainer's toolkit. Okay, first things first. Let's put a name to this problem. It's a fundamental challenge, really. Every single AI practitioner battles with it, and understanding it is the absolute first step to overcoming it. The technical term is overfitting. And honestly, the best way to think about it is like a student cramming for a history exam. They don't learn the concepts, they just memorize the exact wording of every single page in the textbook. So sure, they can answer questions they've seen before perfectly, but if you ask them to explain the ideas or analyze a new historical event, they're completely clueless. Our AI is doing the exact same thing. It's just memorizing the answers instead of actually learning the subject. So, how do we fix this? Well, our first solution involves taming the model's internal complexity. It's a really powerful technique known as L2 regularization, but you might also hear it called weight decay. So the core idea here is pretty brilliant. We basically change the rules of the training game. We add a penalty to the model's score, not just for getting answers wrong, but for becoming too complex. In a neural network, complexity often comes from the connections or weights between neurons getting way too large. So by penalizing those big weights, we force the model to find simpler, more elegant solutions that are much more likely to generalize. Now, there are 2 main flavors of this. The first is L1 regularization. It can actually force some weights to become exactly 0. It's like it's switching off features it decides are relevant, kind of like saying the wall color of a house has 0 bearing on its price. But then there's L2. It encourages all the weights to get smaller, creating a more balanced model that considers all the features without over-relying on any single one. And for that reason, L2 is often the go-to method for better generalization. And this quote just nails it. As researchers point out, it's all about reducing complexity. By encouraging the weights to decay, to shrink down towards 0, we build a simpler, more robust model that's way less likely to just memorize the data. All right, our second solution is a super clever technique that builds resilience through, of all things, teamwork. It's called dropout. And this analogy is just perfect. Think about it. If one neuron becomes the star student, the one that's overly dominant and responsible for everything, what happens to the others? They get lazy, they don't learn robust features, and the whole network becomes fragile because it's relying way too much on that one neuron. Dropout is designed to stop that from ever happening. So here's how it works. In each and every training step, we randomly switch off or drop a certain percentage of neurons. This forces the neurons that are still active to step up and learn the patterns themselves. It prevents any one part of the network from becoming too specialized. And the amazing side effect of all this is that it's like we're training thousands of different smaller neural networks all at the same time and then averaging their results. This ensemble effect is a game changer for generalization. Okay, on to our third technique, batch normalization. Now this one's a little more technical, but trust me, it's one of the most powerful tools out there for making training faster and a whole lot more stable. So to really get batch normalization, you have to first understand the problem it solves, which has this crazy name, internal covariate shift. As a deep network learns, the weights in the early layers are constantly changing. And that means the data being fed to the deeper layers is also constantly changing its statistical distribution. So each layer is trying to learn from a constantly moving target. It makes training really slow and unstable. Batch normalization, or BN, basically acts as a stabilizer. For each little batch of data that goes through during training, it normalizes the inputs to a layer so they have a consistent mean and variance. It's kind of like making sure an athlete always trains under the same stable, predictable conditions. This lets each layer learn more effectively because it doesn't have to constantly adapt to a shifting landscape. And this is what that looks like in practice. These graphs are from the original Google research paper. On the left, without batch norm, you can see the distribution is just all over the place. That's the moving target. But look at the right. With batch normalization, it is incredibly stable. Now, the network has a solid foundation to learn from.
So what does all that stability get you? Pure speed. The authors of the original paper found their model achieved the same accuracy with, get this, 14 times fewer training steps. That is a massive accelerator for deep learning.
Now for our fourth and final technique, which is maybe the most intuitive one of all. If a model is overfitting, well, maybe it just needs more varied practice. And this is exactly where data augmentation comes in. At its core, overfitting happens when a model is just too complex for the amount of data it has. So the simplest solution is just get more data, but that's often really expensive or sometimes just impossible. Data augmentation is this super clever workaround where we take the training data we already have and just create slightly modified copies of it, artificially blowing up our dataset.
For things like image classification, this is incredibly powerful. We can create new training examples by just randomly rotating, flipping, zooming, or shifting the original images. This teaches the model that a cat is still a cat, even if it's viewed from a different angle, or in different lighting, or if it's slightly off-center. The model learns the true features of catness, instead of just memorizing one specific picture of a cat.
So there you have it, 4 powerful techniques. Let's pull them all together now into a kind of comprehensive toolkit for any AI trainer who's trying to build a truly robust model. Here's our toolkit at a glance. We've got L2 regularization, our balanced influence tool that keeps the model simple. We have dropout, the group project, which builds resilience. We have batch normalization to create stable conditions for faster learning. And finally, data augmentation to provide more practice and improve generalization. You can see how each one of these tackles overfitting from a totally different angle. But here's a really crucial point for anyone who's actually building these models. These tools don't always play nicely together. In fact, research has shown there can be a disharmony between dropout and batch normalization. And you might ask why? Well, think about it. The randomness introduced by dropout can completely mess with the stable statistics that batch normalization relies on to do its job. It really goes to show that building great AI isn't just about using every tool in the box, it's about understanding how they all interact. So, we've put together this incredible toolkit to stop our AI from just memorizing things. But this is really just the beginning, isn't it? As these models grow exponentially more complex, learning from, the entire internet, the real challenge becomes how we teach them what's truly important to learn in the first place. Are we just tweaking parameters for a better score? Or are we on the edge of figuring out the fundamental principles of how any intelligence, artificial or not, truly learns?